I'd like to welcome you. My name is Thilo Schumann, and I will try to give you an update for the next hour about on SAE J1939, the current status, and the future outlook, where it may goes in what will happening. Yeah, my name is Thilo Schumann. As I said, I'm with CAN Automation for more than 20 years. I'm an expert in multiple standardization working groups over the time. And I have a little bit shifted the focus. I was doing some of our application profiles within CAN Automation on CAN Open specifics. Over the last more than 10 years, I'm also specialized in safety and security issues. I would always say more specialized in the basic stuff and basic principles than in applications. That said, I'm still also back in the automotive market for some years in terms of our CAN Open specifics profile on special purpose cars for basically for cars converted to taxi usage, blue light vehicles, and yeah, people with disabilities. So that's just for short our my specific little specific background on the topic. As you may know, CAN Automation was established in 1992. Around in 1985, 1986, CAN itself has been published, and in the beginning of the 90s was starting to become an international standard. And CAN Automation was founded to join the activities by different companies and to make it possible to market CAN-based solutions in many different industries. In the first, as the name implies, in mainly the automation industry, but for some times we are now back also in automotive industries and many other industries we haven't even thought about, like CAN is used in electric bikes. Yeah, so it shifted or it broadened our focus, let's say it that way. And we as CAN Automation, of course, try to support besides our one protocol, which is known by CAN Open, also support all the other CAN-based protocols. And so it's today for the SAE J1939. CAN Automation as an organization is right now more than 700 members. So each member represents basically a company. We have small self-employed people, but and we have also big companies like Siemens and Rohde and Schwarz and others. Basically, all the companies doing some kind of business related with CAN. We ourselves, within the organization, together with our members, maintain and develop all the CAN open-related specifications. But we personally are also present in the different international standardization activities, meaning ISC, ISO, and as well as SAE. We try to give also technical support and provide consultancy services and seminars like or information updates like today. If you are interested in the latest news, we publish our CAN newsletter since the beginning. and that's of course also available online. And we have different email updates, monthly updates for everybody in our CAN info mail, for example. Because of European General Data Protection Regulation, or GDPR, if you want any updates from us, directly pushed to you email mailbox, so you have to inform us actively if you want to receive the info mail. So just shoot us an email to our office, and you saying that you would like to subscribe, and you will receive it. We are also present on Twitter and LinkedIn, and just recently on Facebook. What is SAE J1939 and the main features? As you may know, J1939 was also developed early on, or it started also beginning in the 1990s. It is uses the CAN data link layer with frames mainly with 29-bit identifier. It supports peer-to-peer broadcast communication, what is of course used for diagnostics and configuration purposes, as well as broadcast communication, which is mainly of course used for the process control. The original intention, as the SAE is the Society of Automotive Engineers, the original intention was that the protocol is to be used in trucks and buses. Over the years, it's not only used anymore in trucks and buses. It's mainly used for diesel engine control and all the auxiliaries which are required there, which originally, of course, comes from trucks and buses, but it is as such used everywhere where I have diesel engine these days. So it's in maritime electronics, it's in agriculture, it is used in diesel generators and alike. So it's a widely used protocol in all of these areas. As doing this application, of course, so means that it's not only a protocol in terms of how to communicate and how to do network management, but the main purpose, of course, is to define all the application-specific parameters which are required to exchange the data between the different devices to control the process, to control the application, which is mainly a diesel engine and its supplemental devices and auxiliaries. As such, the J1939 protocol is not a single specification. It's comprised of a number of different specifications. If I look at my the ISO layer, at the OC layer model, then I have all the physical related specifications are the specifications which are 11, 13, 15, and so on. So they define, here I have defined the specific physical requirements, like in 11, the twisted shielded pair with 250K of communication speed. We have in the 13, the OBD connector defined, and so on. Of course, then we have in the SAE J1939 the definition to use CAN. Originally only the specification 21, which defines the classical CAN, but for some time we now have specification 22 available, which is related to the CAN FD communication. We have the network layer specification, and then mainly also our application-specific definitions, which is mainly the specification 71, which defines the behavioral application layer. And then added to the 71 is what it's called digital annex, which contains all the parameter definitions, parameter group definitions. So basically all the specific application data and how it should be encoded, transmitted, and the like. Of course, there are also many supplemental specifications for specific purposes using implementation guidelines and the like. I said SAE J1939 uses the classical CAN frame format, and in this case, the CAN-based frame format, but with the 22 specification, J1939 is also ready to use CAN FD these days. So any SAE J1939-based application, which over the years used, of course, the classical CAN-based form, is now able to use CAN FD, which is available also for some time right now. So that makes it useful, because with classical CAN we were limited somehow to exchange a maximum 8 bytes of data, but now with CAN FD we are able to communicate up to 64 bytes of data in one specific frame. How is the SAE is doing it? It's basically not a new invention. They are not. Basically they reuse the definition from the automotive world. So while SAE J1939 is basically mainly used for diesel engine control in trucks, buses, maritime, and so on, we have also other automotive industries, automotive itself, car industry, which is using CAN FD these days. And so they decided already early on how to use CAN FD, how to integrate CAN FD in my current network setup. And of course, automotive is using Autosar and have all the definitions within Autosar. So within the Autosar group, it was thought about how to make use of the larger CAN FD frames with up to 64 bytes with as little change as possible. And so the idea is to have the existing definitions, which is now which is called PDU, so a protocol data unit. And so, and this PDU is basically like a classical CAN frame with data contents of up to 8 bytes. Special header is added. And then we can put a number of those PDUs with the specific header into one CAN FD frame. So that makes it possible to reuse all the existing definitions with only a little change and make use of the higher CAN frames, and with that also the higher bandwidth. And that is just being made by a little additional part in our software stack, which takes care of this packing basically of classical data into the CAN FD data. And with this existing definitions, and most of the truck manufacturers in Europe are also somehow Autosar minded, they requested from the SAE that any SAE implementation specification should be as most likely compatible with the Autosar definitions. And that's what basically happened in a way that that most of those manufacturers meet together under the umbrella of CAA and made a according definition on how to map J1939 parameter groups into the CAN FD data frame with that exact principle in mind, and also how to map all the other required protocols and make that compatible to Autosar. That was released some years ago as a CIA specification, as 602-2 specification. And it was then also forwarded for to the according SAE committees as a proposal on to extend the J1939 specification stack with that specific requirement. And yeah, there was also a proof of concept made by some companies, namely Vector and ZF. They used an existing J1939 network with a retarder and a transmission box, communicated via a specific gateway with this gateway on via a CAN FD backbone and showed that this type this compatibility is possible, and it also helps. And with that proof of concept, they showed basically that an original bus load on the original classical CAN network could be, with a bus load of 50%, could be reduced on the backbone network to less than 9%. So it's a huge benefit, and that's giving additional leeway to put more data on. And that's what we require. We have more devices and more requirements to communicate. And so we need those additional possibilities. The actual version or the CAA specification on this is based on this Autosar principle. So I have my multi-PDU definitions. That's basically the whole CAN FD frame with up to 64 bytes. And this whole frame then contains a number of what we call C-PDUs, or contained PDUs. PDU stands for protocol data unit. And so, and this is the original J1939 definition. So I can reuse all my existing definitions. We don't have to change anything in the application specification. So we don't have to change anything in the 71 specification or in the digital annex of that, and just can reuse all this the same thing. The model looks a little bit like this. Of course, I have an additional, I need an additional software layer and a specific routing layer, and a specific transport layer, which then is basically able to, if I go from the upper layers to the lower layers, which is able to pack the data into a single CAN FD frame or in an MPDU accordingly. And on the receiving side, like it is in this model shown, I need this layer to basically to unpack the data and to forward it on the right services in my application. Here it's shown a little bit more in detail. I have on the reception side, I'm receiving my specific PDUs. So I have a PDU. I have either a multi-PDU with a D PDU, so with a destination PDU, or I have application-specific PDUs which are transmitted in a certain way. And then I have a matrix on how that can be combined, or how they are allowed to be transmitted or packed into the same multi-PDU, or how to unpack them. I have the same with the same with the PG service, and here more in detail. I have my multi-PDUs, and then I have my contained PDUs. And it's a little bit, sorry, I just see it, it's a little bit mixed here. I have already written PG because that what we defined in SAE 6002, that is being accepted by SAE already and is being put in place as a specification. I showed you in the first, we have the 22 specification. And they, and here in the J1939 protocol, now it's not anymore called PDU as such, it's called PG. But it's a little bit different in the naming, but basically it means the very same. I have the same information in my, I have the same information in my address information in my 29-bit identifier as with any classical CAN J1939 frame. It's in the PI field. Yeah. And I have now new services in my SAE J1939-22 definitions. I have my TP, my transfer protocol connections, which have specific PI field definitions. I have my multi-PG container or multi-PDU container accordingly. And I can we can also forward or transmit the Autosar network management messages. So you see, we've done a little progress, or we've gone a long way, while automotive industry with Autosar basically invented the multi-PDU concept. The truck manufacturer said we want that. So we made the CAA specification, and that was then slowly forwarded to SAE, and we now for some time have the according SAE specifications available with the very same definitions, and have compatibility with existing definitions, and can make as such can make the implementation into existing applications much more easily, because we have as little change in the 1939 stack, and we can reuse existing definitions from Autosar. The same is, yeah, that just repeats with the different definitions. We have our digital destination PDU3, which is using the 11-bit identifier. And for even for just using the 11-bit identifier, I have my multi-PG container, I have my Autosar network management, I have my calibration protocol, and I have the ISO-TP communication. The contained PG, or yeah, as in 602, we call it PDU, has its specific header, of course, which identifies the specific information. And then I have my payload. What is also interesting for CAN FD is that each contained PG can have also a specific trailer. That is quite new. We didn't have that with J1939. And the trailer could be either a 4-byte value or even 8-byte value. And then the trailer could be used for cybersecurity stuff. It could be used for functional safety stuff. So I can secure my data in a certain way with the requirements for functional safety or for cybersecurity, or even combine. The specific thing is manufacturer specific. So the OEM has to define its cybersecurity protocol or its functional safety protocol. There is nothing specific here defined. It's just a trailer to be open for different implementation requirements. And of course, we need an additional padding PDU or PG, contained PG, that is required. Like I said, we put a number of basically classical J1939 parameter groups into a single CAN FD frame with additional overhead. So that means we will not be able to fill the 64 bytes completely of a CAN FD frame. So there will always be some, I would say, useless bits in the message. And we need to identify those. And that's then basically our padding contained PG. The CAN FD specific SAE definitions support a new ISO TP transport protocol. New in a way that it now, in a point-to-point connection, allows to transmit up to 16 megabytes with up to 8 concurrent sessions. Or in the connectionless broadcast situation, we can now transmit up to 15 kilobytes with up to 4 concurrent sessions. So we made use basically in the ISOTP. It's like the original ISOTP, but now with longer frames. And as we now have longer frames and the same counters and the same thing, we can just transmit more data. Here's a short example given with a request to send and clear to send example. So I have my original node, which is doing its request to the responder node. We have our timing definitions like in the original ISOTP communication. And then we transmit our CAN FD data frames up to the required number of bytes. And as we now here have also our manufacturer specific trailer available for cybersecurity purposes, for functional safety purposes, and so. The same applies, as I said, also for our broadcast communication with in the transport protocol. It's the same. A little bit different, but the same. SAE made also other specification for CAN FD specifics. So we have the J2284 part 4 and 5, which makes definitions on the physical layer, on how to use CAN FD in automotive environments. What's the requirements here? Like for vehicle application with at 500 kilobits and 2 megabit for the CAN FD data rate. And part 5 is then for as a point-to-point communication with up to 5 megabits. So that that means part 4 is intended like to extend the possibilities with CAN FD, like in existing communication networks. And part 5 is to have a higher speed for the OBD connection, basically, and doing here communication with up to 4 megabits. So we see ISO SAE is having done that in the past for automotive requirements, and now have pushed that also for the J1939 definitions for the trucks and bus. And we have here part 17 for the communication of CAN FD. And as you can see, it's basically very alike and learned from the automotive world again. So it's alike to the J2284 part 4 definition. We have our dedicated timing definitions in the specification. So nobody is left alone and have to make its own experiences, but yeah, just have to use the existing definitions from the SAE specification and make communication possible in the network. So we see SAE J1939 was early on in the CAN area to support automotive requirements in trucks and buses, and to communicate here, to control our diesel engine and to control all the auxiliary devices required in the truck and bus there. And SAE have adopted and developed their specifications over the time with the learnings from the automotive industry to make use of the improvements with CAN FD for that, yeah, to make use of the improvements of CAN FD and to reuse it. But of course, we can't stop here. We need also to push the boundaries forward, and sometimes we also have some open issues, of course, and it's a progress basically. And there is not everything from the beginning. And so within CIA, we have our 601 specification series, which has additional implementation requirements, recommendations, so makes it much more easier to learn from the experiences from the automotive industry and to adopt it for the SAE J1939 applications. One specific thing I want to highlight here is also part 4, our signal improvement specifications. Signal improvement is the problem of ringing, basically. In classical CAN network, ringing was not a problem. You may know ringing basically is if I'm transmitting an edge, I have an edge between 2 bits from recessive to dominant, or vice versa, from dominant to recessive. I always have some ringing. With the jump, I have some ringing. It's not a problem in classical CAN. In classical CAN, we were basically too slow for that to discover such problems, because we switched our bit and did the sampling somewhere late. But with CAN FD, we are getting problems with this kind of ringing because we shorten our bit time. So the sample point moves forward where the jump basically happens. And now ringing can become a problem, and we can see it here maybe a little bit. And then it becomes difficult to detect the correct signal or to interpret the signal correctly if it is a recessive dominant bit or and so on. And so we some work has been done to make signal improvement, which basically means to change dynamically on the fly a little bit the network impedance. And that's been specified in our specification, and their implementations are available from different transceiver chip manufacturers according to the specification to make them to improve on this side, so to improve the robustness and the reliability in the communication with CAN as we have it in the past. So that's a little bit the current status. CAN FD is available for J1939-based application. The specifications are available. We have implementation guidelines. We have some experiences from the automotive industry. And yeah, if you look into the from the automotive OEMs, we have the first cars available with CAN FD. So if you are basically buying a current model from Volkswagen, or then we have CAN FD available there. It's on the roads. And the first heavy duty manufacturers basically started also going into the direction of CAN FD implementing that. So that's basically state of the art somehow. But we don't want to stop there. And so, especially also, again, driven from the automotive industry, I will give a short glimpse on the outlook on what we are working on for the next generation of CAN and how that can be a benefit also for the heavy-duty industry for any of the SAE J1939-based applications. And that's what we call CAN XL. CAN XL is currently in the development. We want to basically have stable specifications by the end of this year. So it's only a few days left, but we are right on track, and maybe it will be January, but yeah, we are right on track on that side. The requirements for the CAN XL is, of course, we want backwards compatibility. So anybody who is doing right now implementing CAN FD as a network should be able to just add CAN XL devices to that existing CAN FD network, and it should not interrupt any communication on that network. We had that problem a little bit in the change from classical CAN to CAN FD. That should not be happening again. And so there is a heavy focus on this backwards compatibility. We will have an 11-bit priority. We have increased the payload again. It can now hold up to 2 kilobytes plus an additional 32-bit address field. Just to add here, this is not so arbitrarily chosen. The idea behind that, of course, is to put in Hall Ethernet frame in. We have introduced virtual CAN ID, so we can make virtual networks, virtual CAN XL networks on the same physical cable. We have a new CRC, a cascaded CRC, and the idea again is we want the same reliability and robustness as we have it with classical CAN and CAN FD. We don't want to sacrifice on that side. We have again our stuff bit rules and these requirements. And what we also have now introduced is a service data unit type. Like we have with the Ether type in Ethernet based networks, so we can run different protocols in parallel on the same cable and can identify those different protocols. With CAN XL, we will distinguish between a priority and an address. So while in all the existing definitions, we had just our priority ID or our identifier, which was 11-bit, 29-bit, and we put in our address information in the same priority. And so with CAN XL, we want to separate those informations. We have a dedicated priority information, and we have a dedicated address information. I said we have a virtual CAN ID, so that means we can support up to 256 virtual networks on a single physical CAN XL cable, basically. So that means that makes it usable for backbone purposes. So if I have my existing classical CAN or CAN FD applications and networks, I can put them on the same backbone and make communication much more easy. And I said we have our new service data identifier, our new SDU type, which allows us to distinguish directly in the frame what higher layer protocol we are using. Does it is a directly mapped classical CAN frame or a directly mapped CAN FD frame, or is it directly mapped Ethernet frame for tunneling purposes? And that just gives us some specific ideas. We haven't done all the work. The specification is currently still in development. Just this morning, I distributed a new version to the group. We want to finalize it in the first quarter of the next year, and maybe by end of next year have also specifically added specific protocols like CAN Open and J1939 and so on. Because currently we push it forward for the specific automotive requirements, but by the end of next year, we want to have it also for other industries, for the heavy-duty industry, for the general automation industry, and so on. I said we have new CRC mechanisms, like in CAN, in classical CAN and CAN FD, we had a single CRC, which helped to secure robustness and reliability. We added on that because you may know CRC is a statistical method. A certain CRC polynomial is only good for specific bit streams of a certain size. And as we know, with CAN XL will support up to 2 kilobytes frame. We have dedicated CRC to security header and for the data to make it reliable. And what is also worked on with CAN XL is a data link layer security. So it's the first time where we'll have security available directly at the data link layer. So the controllers, the CAN XL controllers will implement them directly. It will be a little bit comparable to MACsec, so the security mechanisms used in Ethernet frames. By the difference, it will be directly available in the CAN controller at higher speed, so that the application processor doesn't have to cope with any security mechanisms on that side, and make it a little bit faster. Yeah, that should be about a little bit on the status on for the heavy duty industry, for trucks, buses, for off-road industry, for maritime diesel generators and the like. Everybody basically which is using SAE J1939 in their specific applications. And that shows a little bit the status. So many of the industry classical CAN, the usage of classical CAN as a get-go. The first started in already implementing CAN FD in the agriculture side and the heavy duty side. And the outlook for the next years is also for the future is with CAN XL. So yeah, we have the possibilities to cope with also future requirements, future bandwidth requirements and the like. Yeah, that should give you a short glimpse on that side. Yeah, if you have specific questions, I will be available. You can also send us an email on specific things. I've put here the email addresses. Yeah, and we will try to answer your question. So thank you for your time. Bye.